Looks like we had a quick hiccup in our stream here. That would mean that the group U144 would have 48 elements in it. So we may end up using some technological tools like these increasingly as we go throughout the semester, just when there are things like tricky number theory that we don't want to get in the way of our understanding what's going on with the abstract algebra. That's just a little tip for a way that you can use Sage to streamline your life a little bit here. So I want to return to the original question that we asked, which is, now that we have a better understanding of what this group is, it's the multiplicative mod 30 multiplication group, and it has these 8 elements because these are the 8 natural numbers less than 30 that are relatively prime to 30. Now let's return to the question itself, which asks us to list the cyclic subgroups of U30. So to get that started, let me list the elements of U30 once again, all 8 of them. So they are, respectively, 1, 7, 11, 13, 17, 19, 23, and 29. So these are my 8 elements of U30. Now, what does it mean when it asks us for the cyclic subgroups? So the word cyclic here is important, right? Because anytime you see the word cyclic, the other word that should come to your mind is the word generator. So a cyclic subgroup is going to be a subgroup that's generated by a single element. It's another way to say what we mean when we say cyclic subgroup. Single element. And when you see the word generated, we should always remember that what generated means is it just is generated by the powers. All the powers, where powers, again, is the abstract concept that we get by iteratively applying the whatever my operation is in my group to an element over and over and over again. So it consists of all the powers of that given element. So for example, if you hand me an element, let's say you hand me the element 1, and I want the cyclic subgroup generated by 1. Notationally, we denote that by putting little angle brackets around my element 1. So this is the cyclic subgroup generated by 1. Well, definitionally, again, what this is it's the set of all powers. So it's 1 to the power k for all integer values of k. So every integer power of 1, I pile all those results together, and that set of elements is going to be, it's going to be a subgroup, which we would actually probably want to prove. It's going to be a subgroup, and it's called the cyclic subgroup generated by 1. And to figure out what it is, we just have to, well, let's start by listing out some powers of 1. Well, anytime I raise something to a 0 power in abstract algebra or anywhere else, because of the properties of exponents, because 0 is the additive inverse, a 0th power of something will always give me an identity element. And the identity element here in my group is 1. But then I raise something to the 1st power and I get itself. I raise something to the 2nd power. I get, in this case, 1 times 1. It's going to give me 1. I raise 1 to the 3rd power. And again, all of these are multiplication mod 30, right? That's the operation in my group. But you quickly realize that by taking increasing powers of the number 1, we're never going to get anything other than just 1 itself. And so the cyclic subgroup generated by 1 consists only of the element 1. So another way to think about that is my identity element, which in this case is 1, multiplication mod 30's identity element, is never going to generate any other element of my group except for itself. So this is not a very interesting cyclic subgroup. It would be much more interesting to take a non-identity element like 7 and ask the question, what is this going to generate? What is 7 going to generate? If I take all of the integer powers of the number 7, where these powers are the repeated multiplication modulo 30, what can 7 generate is the question. So to figure that out, I mean, again, we can kind of just do some manual calculation. Maybe we can use some technology to do that real quick, just to save myself a little bit of time. So let's do this with Sage. So what I want is a table, for Sage to list me in a table, and in the rows of my table I want an integer k, and then I want 7 to the power k, but I want to take 7 to the power k mod 30. And the k's that I want to use, let's suppose we just go from 0 to, I don't know, 10. I'm just picking something, right? I just want to see a bunch of powers of 7 reduced mod 30. And we'll see. And I've got some trouble with my Sage syntax. I am much more conversant with LaTeX. Last week in the live stream you got to see me write LaTeX code in real time. Today you get to see me do Sage code in real time, and I'm very much a novice at Sage. But anyway, this looks as though it's done it now. So here are some powers of 7 reduced mod 30. 7 to the 0 power is equal to 1. 7 to the 1 power is equal to 7. 7 squared is 49. Mod 30, that's 19. 7 to the third is 343, which reduced mod 30 is 13. But 7 to the fourth power is equal to 1. And so what you see is right away that pattern, 1, 7, 19, 13, just starts to repeat. So what this is telling me is that successive powers of 7, reduced mod 30, because that's the operation in my group, multiplication mod 30, are going to give me just 4 elements. The elements 1, 7, 19, and 13. So this cyclic subgroup has 4 elements in it, 1, 7, 13, and 19. We also learned something else about 7 as an element of this group in the process of doing this little exercise. Specifically, we found out that when I raise 7 to the 4th power, I end up getting 1, which is the identity element in my multiplicative group mod 30. So that's something else that we can make an observation about abstract algebra. Right? 7 to the 4th power is equal to 1 in this group. 1 is my identity element. And so the order of the element 7 is 4. Has order 4 in the group U30. And remember, the definition of order contains 2 pieces to it. The first piece is that whatever that order is, that power of my element has to give me the identity. So 7 is an element of order 4 in part because the 4th power of 7 gives me the identity. But the other part of the definition says that it is the smallest positive power that gives me the identity. And we can see that again from my table here, that no smaller power of 7 gives me the identity element, other than, of course, the 0th power, which always does. But no smaller positive power of 7 gives me the identity. Not until I get to the 4th power of 7 do we get the identity. So that tells me that the order is not just less than or equal to 4, but the order of 7 is actually equal to 4 in this particular group. By the way, if we do this same exercise, now that we can see what the cyclic subgroup generated by 7 looks like, if I were to ask you what is the cyclic subgroup generated by 13, let's have Sage do that calculation for us. If I replace the 7 that I'm asking for in my table here with a 13, what we notice is that, in fact, we get the same set of 4 elements as we had before. And so the cyclic subgroup generated by 7 is the very same as the cyclic subgroup generated by 13. And that, actually, is an artifact of the following observation. When we were first building the group U30, the question I had asked is, what is the multiplicative inverse of the number 7? And we found out that the multiplicative inverse was 13. So 7 and 13 are inverses. And from that perspective, it's not surprising that 7 and 13 are going to generate the same cyclic subgroup. Because after all, any power of 7, let's say the 25th power of 7, is also going to be a power of 13, namely the negative 25th power of 13, because 7 and 13 are inverses of one another. And so one of the things we can take to the bank here is that the inverse of an element, are always going to generate the same cyclic subgroup. So that's going to save us a little bit of time as we finish up our search here for what are the cyclic subgroups in our system here. So 1 only generates itself. 7 generates this subgroup of 4 elements, which is the same as the set of 4 elements that 13 will generate. What about 19? If I do the same thing once again with my Sage code here, just replace the 13 with 19 and ask it what's doing here. Now we notice that something different happens. 19 to the first power is, of course, 19. But 19 to the second power, 19 times 19, which what is that? 361. When you reduce that mod 30, you already get 1 again. So 19 to the second power is equal to 1. And so 19 generates a cyclic subgroup that only has 2 elements in it. Just 1 and 19. And one of the reasons for that, actually I'd say the reason for that, is that 19 to the second power is equal to the identity element. 19 is an element of order 2 in U30. Okay. So now we have so far 3 different examples of cyclic subgroups of U30. Let me clear out some space on the screen so we can start to list our findings here as we go along. And I'm going to speed things up a little bit now that I think we grasp the concept of what we're looking for when we're looking for a cyclic subgroup. So far, what have we found? We have found that the cyclic subgroup of 1 is just 1, just the identity element. The cyclic subgroup generated by 7, which is the same as the cyclic subgroup generated by 13, its inverse, has 4 elements, 1, 7, 13, and 19. Meanwhile, the cyclic subgroup generated by 19 has only 2 elements, 1 and 19. All right, so what do we still have to do? We've already found the cyclic subgroup generated by 1, 7, 13, and 19. Let's take a look at some of the others. What about 11? What can I generate in U30 with the successive powers of 11? So we'll just go over here, replace our 19 with an 11. We'll evaluate, and we find out that 11 has the same property that 19 had. After all, 11 squared, 11 times 11 mod 30, is 121, which reduces mod 30 to 1. So 11 is also an element of order 2. And therefore, the subgroup consisting of just 1 and 11 is also a cyclic subgroup inside of U30. So that takes care of 11. We can do 17. When we do 17, we find out that similarly to 7 and to 13, we end up with a group of order 4, a cyclic subgroup of order 4. Namely, 1, 17, 19, and 23. And we can reasonably expect, whoops, I'm crowding myself out here. We can reasonably expect that that will remain the case for the cyclic subgroup generated by whatever the inverse of 17 is in this group. And I don't off the top of my head know what the inverse of 17 is, but we can just forge ahead here. Well, we know it's not going to be 19. We've already taken care of 19 over here, so it must be 23. Let's just check that the cyclic subgroup generated by 23 gives me the same thing as a cyclic subgroup generated by 17, and indeed it does. Right? The elements are 1, 17, 19, and 23 in no particular order. And that means that now the only element that we haven't investigated is 29. What about the cyclic subgroup generated by 29? Evaluate that. We find out that 29, much like 19 and 11, is an element of order 2. And therefore, just 1 and 29 belong to the cyclic subgroup generated by 29. So this list over here on the left is a list of all the cyclic subgroups of U30. So don't be fooled by the fact that I'm using Sage here to do these calculations. That's just because I don't want to pull out a calculator and do 29 times 29, divide that by 30, take the remainder. Just to shortcut the calculations, you can use a computer algebra system like this one. For those of you that are currently my students, if you're a math major with me here at Bridgewater, one of the courses that is part of your major is a programming computer algebra course, and Sage is sort of rapidly becoming the lingua franca of open source computer algebra. So this is a free online tool that you can use to do a lot of great computer algebra sorts of tasks. So we may end up using it more and more over the course of the semester, as I was saying. So we've talked now a lot about these U groups, but I want to farm this for one more question out of this, which is this group U30 a cyclic group? So now that we've seen all of the subgroups generated by all the various elements in U30, what light does this shed on whether U30 is a cyclic group? Well, let me take my Sage off of the screen here. Is U30 cyclic? Well, one of the ways of answering that question is to look at the orders of all of the elements inside of my group. Because in order for a group to be cyclic, there has to exist a single element that's capable of generating by its powers all of the elements in my group. Right? That is the definition of the whole group being cyclic. Right? And in order for that to happen, there has to be an element whose order, as an element, agrees with the order of the whole group. But having the list of all the cyclic subgroups now gives me a shortcut to listing the orders of all of my elements, because the order of an element is the same thing as the order of the subgroup, the cyclic subgroup, that it generates. So the order of the element 1 is 1, because its cyclic subgroup has only a single element. But the order of 7 is 4, because its cyclic subgroup has 4 elements in it. 11 is an element of order 2. 13 has order 4. 17 has order 4. 19 has order 2. 23 has order 4. And 29 has order 2. So there are the orders of all 8 of my elements of U30. And none of them have order 8. In other words, no single element in U30 is evidently capable of generating the entire group. After all, what we did is we listed exactly what each of these elements does generate. And none of my cyclic subgroups here gives me the entire group U30. So no element of U30 generates the entire group. We're going to talk a lot more about cyclic groups in Chapter 4. But because this was a good opportunity for us to talk about the idea of order, and also to get some more practice getting familiar with the U groups, we talked a little bit about this here. But this is definitely a topic that we're going to hang on to. And Chapter 4 is largely going to be about these multiplicative groups. Because it looks like we can get a lot more interesting structure out of the U groups than we can get out of the Z groups. And ultimately, when we get along to chapters 8 and 9 later on in the semester, we're going to be able to make some explicit relationships between U groups and Z groups. For now, they seem a lot more mysterious. It seems like there's a lot more interesting stuff that can happen in the U groups than what happens in the Z groups. And I would say that that's definitely true, because multiplication seems like it's got more up its sleeve than addition does. I'm going to take about 30 seconds to pause, and then we're going to move forward and begin looking at some subgroup tests. We're going to do that by looking at a specific group, which is what we call a quadratic extension of the rationals. So I'm going to take a quick pause. If there are any questions in the meantime, please do contribute those into the Slack channel, and then we're going to take a look next at the group Q radical 2. All right, so what I want to do next is take an example of a problem that's going to give us an opportunity both to choose and apply a subgroup test, and those are a test to determine whether or not a given subset of the elements of a group forms a subgroup or not. And then we're also going to use this as an opportunity to, again, get some practice writing up a proof. So we're going to do a little napkin version, and then we'll do a formal proof write-up version. So here's the question. And this, again, comes from Judson. This is exercise number 8 in his chapter 3. So he gives us a subset of elements of R star. So R star is the group of real numbers, and the operation is multiplication. So real numbers under multiplication. The real numbers under multiplication, with one exception, that we have to take away. That's what this little star up here is doing. We have to take away 0. For the same reason we had to take it away when we were talking about the U groups, because 0 is never ever going to have a multiplicative inverse. So if multiplication is going to be our operation, we need to take 0 and just kick it to the curb. So the set of non-zero real numbers with the operation of multiplication. And the problem is giving us to consider a subset. The subset that consists of all the real numbers that have this form. A rational number plus a rational multiple of the square root of 2. And the square root of 2, we don't know what it is. I mean, we can sort of assume for our purposes that it is a real number, and therefore that this is going to be a subset of R star. All that we really need to know is that it is some number, some entity, which when we multiply it by itself, gives me the rational number 2. Okay? That's all that we need to know about this symbol that I wrote down on the screen, square root of 2. Okay? All we need to know about it is that its square is equal to 2. And so the question is asking us to prove that this subset of R star is in fact a subgroup of R star. Now remember, to prove that something is a subgroup, using the definition of subgroup, we would have to go all the way back to all 4 of the properties: closure, associativity, the identity property, and the inverse property. We'd have to verify all 4 of those things by hand. But I don't want to do that. I want to work smarter rather than harder. And the subgroup tests that we learn in this chapter are a perfect way to work smarter instead of harder. There are 3 different subgroup tests that we can bring to bear. One of them is the one-step test. I'm just going to give a quick little rundown of them before we implement any of them. The second is called a two-step test. And the third is called the finite subgroup test. And each of them has a very careful logical formulation that I want to make sure that we get for the record down here. So let's write down how each of these works. The one-step subgroup test says that H is a subgroup of G. So I'll write it using our notation here. If for all elements x and y in my subset H, we have that x multiplied by the inverse of y belongs to H. That's the one-step subgroup test. So in other words, if you hand me a set, and that set has the property that any 2 elements I pick out of it, x and y, if I replace y by its inverse and multiply it by my x, that product remains inside my subset. If my subset has that property, then that subset is more than just a subset. It's a subgroup of G. So that's the one-step subgroup test. For the two-step subgroup test, what we end up verifying is actually 2 of the OG properties, the original properties of a group. We verify separately the closure property and the inverse property. So if for all x and y in H, we have 2 things to be true. xy belongs to H. In other words, H is closed under the operation of the group G. And also, x inverse belongs to H. So that the inverse property is also satisfied. basically, what the two-step test is kind of telling us is that if we can verify closure and inverse, that identity comes along for free, and so does associativity, and therefore we get everything that we would need for a group. So in a way, the two-step test is not too surprising, because after all, if we took the y in this to be the same thing as x inverse, then x times x inverse belonging to h would mean the identity belongs to h, and therefore the identity property is satisfied. So the two-step test is not that far off from the work we would have to do to verify all four of these criteria anyway, but it's a little bit shorter, and sometimes the two-step test is a little easier to work with. Finally, the finite subgroup test says that if H is a finite subset, then we only have to verify the closure property. And for all x and y in H, we have xy belongs to H. Okay. So those are my three subgroup tests. They're logically equivalent to one another, which means that we'll never have to use more than one of them at a given time. If you can be successful in using any one of them to demonstrate that its relevant property holds for the subset that you're looking at, that one test will be enough to prove that H is a subgroup of G. It's good to get some practice using all three of them, though, because different scenarios might call for different ones of these subgroup tests to be the most natural one to use. I tend to gravitate towards the one-step test, except in the case where I know I'm working with a finite subset. If I know I'm working with a finite subset, I tend to gravitate toward the finiteness test. The two-step test, again, I feel like it is not that different than verifying the properties just manually, going to the original definition. So those are our three subgroup tests. And what I want to do is I want to give us an opportunity to implement one of those subgroup tests to answer this question. How do we know that this subset of R star, non-zero real numbers with multiplication as the operation, is indeed a subgroup? So again, kind of want to do the two different versions. The version where we sort of write it on a napkin, figure out what is the calculation that we need in order to make this work, and then we'll also try to write it up as a formal proof. So let me get a napkin thrown down onto our screen here, and then we can sort of commence the process. All right, so I want to try to use the one-step test. And the reason I don't want to try to use the finiteness, my other favorite test, is that it's not clear to me whether or not this subset is a finite subset. In fact, we can pretty quickly convince ourselves that it's not. Because if A and B are quantified over the rational numbers, well, there's infinitely many rational numbers A and B that we could choose from. And therefore, there's infinitely many different elements in this subset. So we can't use the finiteness test, even if we wanted to. So let me set up on this napkin for a one-step test instead. So in the one-step test, you give me an element X, you give me an element Y. And my job is to show you why X times Y inverse belongs to H. So this is how I'm going to kind of set up my napkin here, right? My X needs to belong to H, my Y needs to belong to H, and then I need to figure out how to do XY inverse. All right, so then I ask myself, well, if X belongs to H, what does that tell me about X? Well, it tells me that it takes this form, right? A plus B radical 2. So let's call that my X, A plus B radical 2. All right, so there's my first element. Y is also going to have that form, but now instead of A and B, I need to use different symbols, because probably the two rational numbers that make up Y are different than the ones that made up X, so I'll call it C plus D radical 2. And now my degree of difficulty is going to be to understand how to compute X times Y inverse. Like how do I find out what X times Y inverse is? To do that, I'm actually going to move to a second napkin here, because we're going to have a little bit more calculation to do. So I'll just put the second underneath the first. Now what, as real numbers, how would I do this? X times Y inverse as real numbers. This would be the same as X divided by Y. After all, the operation in R star is legitimately multiplication of real numbers, the familiar multiplication that we're used to. So we can get away with calling this division, despite all of my warnings about thinking about division. So what is x? X is a plus b radical 2. Y is c plus d radical 2. But what I want to understand is, why is this thing, this weird-looking fraction, how do I know that this is an element of g? How do I know that it can be written as a plus b radical 2 for some rational numbers a and b? Because that's not what this looks like right now. Okay. This is probably the first time since you took Algebra 2, by which I mean high school Algebra 2, not abstract Algebra 2, that the thing we need to know how to do is we need to know how to rationalize the denominator of this fraction. How do you rationalize the denominator of a fraction? You multiply by what we often call its conjugate. The conjugate of c plus d radical 2 is c minus d radical 2. That turns out to be exactly the tool that we need to do this computation. Because once I've done that computation, my denominator, c plus d radical 2 times c minus d radical 2, that's going to be c squared minus 2d squared. It's a difference of two squares. FOIL it out. Do whatever you need to do, right? But the important piece is that c squared minus 2d squared, that's a rational number, because c and d were rational numbers to begin with. Meanwhile, upstairs, I'm going to get ac minus 2bd plus bc minus ad radical 2. So I just did a bunch of high school level algebra, right, to simplify out these products. But the point of doing that algebra is as follows, is that I've just convinced myself why it is that xy inverse has exactly the form that we wanted it to have. C squared minus 2d squared. Put in a plus right here, right? Because this first thing, because a, b, c, and d are all rational numbers, this first thing here is all rational. And this second thing here is also all rational, right? Because a, b, c, and d are all rational numbers, this combination of a, b, c, and d is a rational number. That combination of a, b, c, and d is a rational number. And therefore, this has the form rational number plus rational number times radical 2. Therefore, this belongs to G. Cool. That's exactly the observation that we needed. Sorry, it's called, yeah, sorry, I'm switching notations here. Let me choose a notation and stick with it. I tend to use H as the names for my subsets and subgroups, so I'm going to change the original statement of the problem to reflect that. So we'll call this H instead of G. Anyway, and so that's what it is then. How do I have this written here? AC minus 2BD over C squared minus 2D squared plus BC minus AD over C squared minus 2D squared radical 2. And that is evidently an element of H. So that's the napkin version of this proof. What I actually need to do is take a quick pause for just a minute or so here. We'll come back and we'll do the write-up version. I want to translate this into an actual written-up proof. We'll do that right after the break.